Hello, Physics 1. All right, so welcome to Tuesday's lecture. We're going to be continuing in Chapter 9, looking at the energy system. Now we're going to be comparing two models of a system. So we've talked a lot about the point particle model, which is what we have used for the majority of this class. So we have done some work with the extended model, and we're going to be comparing it to the extended model and to see how we can use both of them together to fully learn about the motion of a system. So compare point particle model to the extended model. And we're going to see how they can play together. Because both of them have their uses and applications. So it's not that either of them is wrong, it's that they give you different types of information. Okay, so let's look at point particles. Let's say, okay, so we've got something that looks like this. The center of mass is, I don't know, here. It's got some forces acting on it, different locations. So this would be what the extended system would look like. And if you were to draw a model, it would look like this. So you need to account for where all the forces are acting, and you need to know where the center of mass is. Okay. Now, if we were to do the point particle model of the system, so we do a point, we're going to assume everything's acting on the center of mass. So I've got a force going down, a force going up, a force off to the angle, and a force to the horizontal. So this is our point particle. And this is really going to tell us a lot about the movement of the center of mass, which is an important part of our energy equations. So, going on with the point particle model, so we know that the change in momentum of the system with respect to time is equal to F net. And of course, for those of you in the algebra class, this is just delta P system over change in time. Translational kinetic energy, which is the movement of the center of mass, is equal to the momentum of the system squared divided by 2 times the total mass, which is equal to 1/2 mv squared, where we're looking at the velocity of the center of mass. So we're starting to see how we can bring the energy principle and momentum principle together to learn more about a particular system. Okay. So, work and energy for a point particle. So we have the change of translational kinetic energy is equal to F net over the distance that it's applied. And for this, you assume F net is constant during displacement. Else, use an integral or an easy summation. So we have talked about it where you've got like the little steps. So that's kind of how that works. And so we can see we have joined together the joining of the momentum principle and the energy principle. So you can use the momentum principle to go after F net, and then you can, once you have that, you can go after kinetic energy translational, which is a part of the energy principle. Pretty cool, hey? Now let's look at extended objects. So, point particle models, basically they can translate and the center of mass can move and you can do work on them. There's a lot, they can't rotate, they can't twist, they can't vibrate, they're one-dimensional objects. Everything that if you want to go to or more dimensional, you need an extended objects, which allows you to look at things like that they can rotate, they can vibrate, they can change shape, and have different parts move different distances. You want to learn any of these things, you need the extended model. And this, of course, is not a comprehensive list. Okay, so, for example, if you want to look at the spring and you want to take into account the stretch, you need the extended model. If you model it as a point particle, all that's going to happen is, well, the center of mass might be moving around, and that's all you can do. Can't take into account all this stretching. Okay, so for extended systems, we need to think about where the force is being applied. So work might look different for the extended model. And we'll look at that. So the change in energy of a system is equal to the sum of all of the forces acting on the different parts over the displacement of where they're acting. And again, this assumes Fi is constant over the interaction, else you do integrals. And if you do take a classical mechanics class, you will do that a lot. But by that time, you're so practiced at it that it becomes second nature. Okay, so let's talk about somebody jumping and how we can bring the point particle model and the extended system together. So normally this is where I'd stand in front of the class and jump. This camera only points down. So let's say I'm going to do a horizontal jump with my hands. So you crouch down, your feet are in contact with the ground, and then you extend upwards and eventually you leave. So during this particular interaction, so I'll do it vertically, it's not as good to see, but you've got the normal force from the ground, and then you've got the force of gravity acting on the center of mass. And from crouch to jump up, the center of mass moves. Okay, so modeling a jump as a point particle. So we'll have our center of mass. So that would be about in the middle of your body. And for me right now, it is very obviously in the middle of my body. By that, I'm referring to how large my midsection has gotten. It is full of baby. So we have the force of gravity pulling down and the normal force acting up. Remember, with the point particle model, all forces are acting on the same location. In reality, they're actually acting in two different spots, but we've condensed the whole system together, acts in one spot. Okay, so during the jump, the center of mass moves during the interaction. While being acted on So we are looking from the initial crouched and at rest and final stretched out displaced H and feet in contact with ground. In contact with ground and in motion. So you're getting ready to jump. So we're not looking after the feet leave the ground. And that's because we want to keep the forces constant the whole time. Okay, so the change of translational kinetic energy is equal to work. The change of translational kinetic energy is equal to the net force times the displacement of the center of mass. Oh, I guess I called it R. There we go. No, and then I called it H. Okay, never mind. All right, so we have 1/2 mv squared cm minus 0, because it started at rest, is equal to Fn minus mg times h. That's the distance that the center of mass has moved. So you start here, you end here, initial, final, h. And if we were to go after the feet leave the ground, so Fn goes to 0 upon jump. So we don't want the force to change. We want to use the easy formulas. So we're going to just say it goes until the very moment before your feet leave the ground. Okay, so we know translational kinetic energy. It's equal to mg times h. We could even write this. We could go after, say, velocity. That's going to be equal to Fn minus mg times h. You could easily solve for velocity. So this is important. If we need a complete energy principle, we need to know about the center of mass. So it was important to take the point particle model. Okay, but there's limitations to it. There's valuable information, but limitations. Just like there's limitations to the extended model. We can't learn about translational energy from it. All right, so let's look at the jumper as an extended system. And what could we learn? We could learn about thermal energy. We could learn about arm and leg movement. And we're going to be doing all of this theoretically and then move into examples where we can make actual calculations. Chemical, depletion of energy, all kinds of stuff. All right, so you might be asking, is the work the same? No. We need to look at where the force is applied. Okay, so let's draw our model. Here's our person. You look like this, right? So we've got the normal force. Let's make it an orange. Acting on the feet. Remember, gravity still acts at the center of mass. So gravity is going down. Man, orange and red look very similar. So 2 different spots. All right, let's analyze the jump. Okay, so using the extended system, we have the energy of the system is equal to the sum of all the forces times, or dotted with all their little displacements. So we would have delta K translational plus delta K relative plus delta E internal is equal to mgh plus Fn times 0. So remember, your feet are in contact with the ground the entire time. So while they are experiencing the normal force, which is non-zero, it is being applied over zero distance. The movement of the center of mass no longer means that the normal force is no longer doing work on you with the extended model. So let's write a couple other things that we've learned from this system out. So, all right, start with that one. So foot doesn't move, foot. So Fn acts over zero distance. So delta K relative includes rotation of arms and lower legs. Delta E thermal contains internal increase of thermal energy, decrease of chemical energy. So when you jump, you get hot and you burn calories. There you go. And none of this appeared, and none of this was in the point particle model. All right, so let's combine the two models. So delta K translational plus delta K relative plus delta E internal is equal to minus mgh. So we can replace this. We know what that is. So we would have Fn minus mgh plus delta K relative plus delta E internal equals minus mgh. Oh, we've got an mgh on both sides. They're both negative. Therefore, delta K relative plus delta E internal is equal to minus the normal force over the height. And that's as far as we can go with this setup. This is all theoretical, just to help you see what you can learn. And we wouldn't have been able to make this connection if we wouldn't have done the point particle model first. We needed both systems to go after this result. All right. Moving on to another example. Pulling a spring. So you take a spring and you apply a force to each side. Let's say it's an even force. Okay, so as a point particle, you've got a spring, so I'll draw a little picture too. So the spring's being pulled by a left hand and a right hand with equally applied forces. So you would have the right hand, and you would have the left hand. And in this particular case, F net is equal to 0. They're equal forces in opposite directions. So and therefore, the change of position of the center of mass is equal to 0, and therefore the change in translational kinetic energy is equal to 0, 0. Okay, so not super exciting as a point particle. That's fine, but we still learned something. Let's look at a spring as an extended object. So the change in energy of the system is equal to the sum of all the little forces over the distances to which they are being applied. So we would have the change of translational kinetic energy plus the potential of the spring is equal to the left hand applying a force over the change of position to the left plus the force from the right hand times the change of position to the right. So in this case, where this is being applied is important. And we can definitely see displacement. So both hands do positive work. Because the energy of the system is increased. Okay, so going back to our previous calculation, so we know we have the change of translational plus the change of potential we know this is 0, so we would have delta 1/2 KSS squared for the spring is equal to the force from the left hand over the left side displacement plus the force from the right hand times the displacement to the right. So what we can see from here is the point particle model gave us that this was 0, no change in kinetic energy, and the extended model gave us all of this. Again, both were needed to fully analyze this object. So let's look at how to do this, and I'm going to write out a couple of steps for you to keep in mind. So for the point particle model, you need to assume entire mass concentrated into a point at the center of mass. You need to assume all forces act at that point. And then you define displacement. Then you calculate the network on the point particle. And use that to find the change of translational kinetic energy. Then for the extended object, Oh, and draw a diagram. Very important. All right, and you'll need to then draw a diagram for the extended system. This one will need to depict where each force is acting. Identify the displacements for each force and calculate the work done on each point. And then you're going to use our friend the energy principle to find delta E. And then you put them together for the whole picture. All right, so let's do an example. We have a thin box in the Kuiper belt. So we are in space, and it contains a mass of clay of mass m connected to a relaxed spring with a coefficient Ks. And the mass of the box and spring are negligible compared to the clay. Initially, the box is at rest. Then, a constant force is applied. And the box moves a distance b, and the clay sticks to the other side. Stretching the spring S. All right, so let's draw some pictures. Here is where we start. Here's our clay on the spring of Ks, and then the force is applied, moving it in that direction. Moving it some distance, some stretch S, and so from here to here, we are looking at B minus S because the spring started out here. Okay, so draw some more pictures. So initial, and final. Okay, so this is what you need to keep in mind as we begin to solve this problem. Let's go after how fast the box is moving, and the increase of thermal energy of the clay. And we're going to neglect Q. We don't really have any information to go after Q, so that's a pretty good indicator. You can safely neglect that. All right, so to go after speed, we need to use the point particle model. All right, so our system is going to be a point particle. So the only thing that really has mass that we are counting is a point particle of the clay with mass m, and the surroundings is that force F. We don't know what it is, but we know it's there. The initial state is at rest, and the final state is a particle with speed v. All right, so the energy principle for the point particle model, where you can only go after translational kinetic energy. So the change of translational kinetic energy is equal to the force over that displacement in x of the center of mass. We know the displacement of the center of mass is equal to b minus s, because the spring started with some stretch, and the b had to do with the entire box. So we have 1/2 mv squared minus 0, since it started at rest, is equal to force b minus s. Velocity is equal to 2 force b minus s over m. All right, so also, I'll write this out explicitly. This is equal to f b minus s. So there's 2 bits of information that we learned from this. Okay, so if we want to go after the internal energy, we're going to need the extended system. So let's do the extended system next. I'm going to quickly box this. I would recommend you box these in your own notes, and definitely on quizzes and tests. So our system here is the mass, the box, and the spring. The surrounding external object exerting force F. It's initially at rest. And the final state, moving with speed v is equal to 2f b minus s over m. And we found this, of course, from our previous point particle model. See, very useful. All right, using the energy principle, the change in energy of the system is equal to the work. So we have the change of translational kinetic energy plus the potential of the spring plus the change of internal is equal to FB. So the force is being applied to the box over distance B. And if you recall, the change of translational energy is equal to FB minus S. So we have FB minus S plus 1/2 KSS squared plus delta E internal is equal to FB. Delta E internal is equal to FS minus 1/2 KSS squared. So once again, we've got FB on both sides. That's where that went. And when we brought everything over that wasn't the change in internal energy, which is what we were after. So just a note, when you're doing these, the trick, you need diagrams, good labels, and good problem setup. These are the keys. All right. All right, so we will stop Tuesday's lecture here and see you next time for part 2.